review session. This is the last actual class meeting, so it's been a great year thus far, a great semester, and I hope everyone does well on the final. And in order to help that, of course, this is a review session, so what I'd like to do is entertain any questions you've gotten thus far from any of your stuff. Anything you want me to present or talk about. Yeah?
I don't have a specific problem with it, but can we go over implicit differentiation?
Implicit differentiation? Sure. Let's certainly do that. Implicit differentiation, section 3.5. First, give you a little bit of an overview, reminder what it was. I'm going to do some problems. Okay, so implicit differentiation, the idea is that you're taking derivatives of a function defined by an equation f of x, y, and your goal is to obtain dy dx. This function f of two variables is the thing that defines the relationship between x and y. This f here is two variables. It's telling you something about x and y. And the relationship between implicit differentiation and regular old differentiation comes about like this. Comes about something like this. You have a function that says y is equal to, say, g of x. Well, how do we get it into this form? We'll move the y over to the other side. Move the y over to the other side. And then what we're doing is we're saying, let f of x and y be this expression. And so when we take regular old differentiation, you could really think of it as a special case of implicit differentiation. It's really a special case. Okay, so how do you do it? Well, it's probably best shown by example. And let's grab an example from your book. Well, maybe let's look at number 13 in 3.5. And this one says the following. It says 4 cosine of x times sine of y is equal to 1. You can see it's just about in this form here. Instead of it being equal to 0, it's equal to 1. You can fix that by moving the 1 over to the other side. Doesn't really matter too much. The idea is you just take derivatives of everything in sight and use the chain rule to keep track of things. So take derivatives of both sides to x and use the chain rule wherever you see a y, which you think of as a function y as a function x. Okay, so let's see how that works. So we're going to take the derivative of the left side first. And let's see here. I have a product of two functions, so I should use the product rule, I think. So we take the derivative of this side, and I'm going to use the product rule here. Okay, so what does the product rule say? It says I should take the derivative of this times this plus the derivative of this times this. So let's see, I guess that is 4 sine of x times sine of y. That's derivative of this times sine of y. Now I'm going to add to it this left alone times the derivative of this. What's the derivative of sine? Cosine. And I see that I've already made a mistake. That's my mistake. Yeah, I need a negative. Right. Good catch. Thank you. Okay. So let's see. Now that's the derivative of the left side. Now what's the derivative of the right side? Derivative of this. 0. Yeah. Now, do we finish writing this out? We finished writing this expression out. No. Right. See, this is the most common mistake that one makes when using implicit differentiation and when you're using the chain rule. Because remember, this y is a function of x. Here we took the derivative to get our cosine, took the derivative sine of y of x. This is cosine y of x. So we need to multiply this whole thing by the derivative of that. So do not forget that sort of thing. Of course, don't forget the minus signs when you're taking derivatives of cosine, but definitely when you're doing implicit differentiation, the thing that needs to be on your brain the whole time is, where do I use the chain rule? Okay. So now that we've got this all set up correctly, we've got all the pieces in there. Now, well, we wanted to find the derivative of y with respect to x. And we've got all the pieces we need now. We have an equation. This whole expression is equal to 0. So we can solve for dy dx. So now to solve. We solve for dy dx. Well, let's see. I guess we want to move this term over to the other side. So we have something like 4 cosine of x, cosine of y, y dx. And that's equal to, I'm going to move this over to the other side, so I'm going to lose the minus. 4 sine of x, sine of y. Of course, I'm solving for dy dx, so I'm going to move the entire coefficient out front over here, over to the other side. So this is sine of x, sine of y, divided by cosine of x, cosine of y. Okay, that's an entirely nice answer, sort of perfectly valid. You could notice, if you are so inclined, that sine of x over cosine of x is equal to what? Yeah, it's equal to tangent of x. So this is tangent of x, tangent of y. If in the initial stages of this problem, over here, you were able to solve for y, you wouldn't actually need to use implicit differentiation. It's not entirely necessary, strictly speaking. But then you can get rid of this y and write it entirely in terms of x. In this case here, solving for y is somewhat of a pain. You get these inverse signs floating around. So it's probably just perfectly best to leave it alone. Question, yeah?
What part of that equation do you use the chain rule?
Where do we use the chain rule? That is a good question. I was trying to use a little bit of dramatic draw out there by leaving it off. The place that I use the chain rule is right there. I'm going to be a little more explicit with this. Be a little more explicit with writing out this product rule here. So what we did is the product rule says what I'm going to be writing down is this expression. This is sine of y x. Now, the derivative of this thing here is the negative 4 sine of x. The derivative of this, however, is not just cosine of y, because y depends on x. It's, think of it sine of something. What's the derivative of sine of something? It's cosine of that same something times the derivative of the something. And that's where the change will be. You see that? Other questions? Okay. That answer your need for implicit differentiation? Would you like to see another?
That's good.
Okay. Yes, sir. Sure, logarithmic differentiation. Absolutely. Right, let's see if we can find a good example of logarithmic differentiation. Do you have one in mind? No. Well, let's see here. There is, perhaps the best one to keep in mind, this is an old favorite. So, logarithmic differentiation is a kind of implicit differentiation. Kind of implicit differentiation, where the first step is to take the log of both sides. And probably the most common places where you'll see logarithmic differentiation playing an important role is in a problem like this. So you can detect that logarithmic differentiation is necessary when you have an exponential function in which the base and the exponent vary. So if both the base and the exponent are functions of x, then that's when you need to use logarithmic differentiation. So that's how you detect it. There are lots of good examples of this sort of thing. I'll make up a simple one. A simple one, like maybe y is equal to sine of x to the sine of x. What you can't do is you can't do power rule, because the exponent is changing. What you can't do is you can't use the derivative of like an exponential function because the base is changing. So you have to do something different. And the logarithmic differentiation is the right idea. So what you do is you start out, the first step is take log of both sides. So the left side, that's easy. That's natural log of y. And just to be perfectly explicit about this, I'm going to write of x to remind you that this y is a function of x. Now I'm going to take a log of this side too. Now, the nice thing about logarithms and exponents is logarithms turn exponents into multiplication. So this exponent here turns into a multiplication. Okay, once you've done that, now there's no exponents floating around. Everything is more or less amenable to your usual rules of differentiation, except for the fact that the y has been buried inside the logarithm. Yeah?
Is it the base or the exponent that's going to
Oh, that's a good question. I will color code it. Make sense? So the exponent has gone out in front. Okay. So at this point now we use implicit differentiation. Okay, so let's go with that. So we want to take the derivative of natural log of y. What's the derivative of natural log of something? 1 over something, right. So we get 1 over that something, but we have to use the chain rule. So we multiply it by the derivative of that something is y. Okay, on the other side, we need to take the derivative. And let's see, I have the product of two functions, the product of sine and the natural log. So that's the product rule. Okay. And doing a little more simplifying here. Let's see, what's the derivative of sine of x?
No, cosine.
Cosine of x, right. No minus signs. And let's see, we just had to deal with the derivative of log of something. We said it was 1 over something. Okay? 1 over something times the derivative of the something. Okay? So this is something we can simplify. Let's see, these signs cancel. Derivative of the sine we just figured out a moment ago, that was cosine. Okay. So all the calculus is now done. It's just a matter of solving for dy dx. Solve for dy dx. So that's just y of x times this expression. And because we started out with a formula for a function of x, y is a function of x, we started out with this formula, we know what y is. So we can replace that y right here with what we already know it to be. And there you have it. All the calculus is done. You could simplify this slightly if you, say, wanted to take out the factor of cosine. It's entirely perfectly valid to leave it like this. I'm happy with this on the exam. If you get this far, it'll be thumbs up. Okay. Answer your question there? You think so? All right. Good. Okay. What else? Related rates. Sure. Okay, related rates. And related rates are section 3.9. In your book. Now, I had mentioned yesterday, and I maintain this point, that on our final, I'm not focusing on applications very strongly. Now, most of the related rates problems are applications. Things saying, If I have a bowl of water filled up to the brim, I puncture the bottom of it, how fast is the water level drip, that kind of thing. Not aiming for that. But if there's a little bit of geometry or something like that, then that's fine. And I may ask that sort of thing. So for instance, I might ask the kind of question like this, like number 8. And it says, suppose that I have a function, and it's defined implicitly. So suppose x and y are related in this way. So there's some kind of functional relationship between x and y, at least for some choice of values. Although maybe in general there might not be. This might just be a relationship. Okay. Now, what we're going to do, though, is we're going to make the assumption that both x and y are functions of t. So thus far, we just know they're somehow related. Now I'm going to give you a little piece of information and say x is actually a function of t, and y is actually a function of t. So these two functions are related in some fashion. They're related through this equation. And then they say if they give you a derivative, the x dt is equal to 1/3, find, oh wait, that's dy dt, my bad, x dt, when x is equal to 2. And y is equal to 2/3 squared. Okay, so the idea of related rates is two things. It's usually a combination of the chain rule and implicit differentiation. And implicit differentiation, of course, uses the chain rule anyway. So it's really all chain rule in action. So first of all, let's sort of step back and ask a few questions about what this problem is got under the hood. First of all, what kind of curve is this equation describing? Well, it's kind of like a circle, isn't it now? But there's like, if it were a circle, it would be what? X squared plus y squared equals something. It's not quite x squared plus y squared equals something, now is it? I could try to clean it up, right? I could try to make it into x squared plus y squared equals something. But I wouldn't succeed. Right, like I could divide both sides by 4. I could say x squared plus 9/4 y squared is equal to 9. Not quite a circle. What is this? What is it? It's not a circle. It's like almost a circle, though. Yeah, this is an ellipse. This is the equation of an ellipse. In fact, it's probably worth writing this down. Here's an ellipse, somewhat badly drawn, but an ellipse just the same. If this is A, this is minus A, this is minus B, this is B. Well, the equation of this ellipse is given by x squared over a squared plus y squared over b squared equals 1. So that's the equation of an ellipse. Now, how can I make this ellipse into a circle in general? How would A and B have to be related? Yeah, they have to be equal, right? They would be a circle. If A and B are equal, A and B are both the radius of the circle then. These denominators would be the same. I can push that common factor over to the other side. They get x squared plus y squared equals a squared. So it would look just like your equation of a circle. So this is a generalization of that idea. So this thing here, A is what? What is A in this equation? Well, remember, I've got to do a bunch of manipulations here. I've got to make the right side equal 1, and I'm looking at the denominator square root of it. Okay, so let's rewrite that. So this is supposed to equal 1. So I'm going to divide both sides by 36. So what's 36 divided by 4? Yeah, but I want to know the denominator. 9. Okay. And what's 36 divided by 9? Yeah. Okay, so this is the same guy as that. So this situation here, what's A? 3. A is 3. And what's B? 2. So this is an equation of ellipse whose sort of horizontal radius along the x direction, if you will, is 3, and whose vertical radius is 2. So that's what this thing is. This thing is an ellipse. So what this is saying, suppose that we've got some function of x and y, so that whenever you look at them, x and y end up lying on this ellipse. So we've got an x of t, y of t, is a point on this ellipse. And it's changing with respect to t. It's in motion. Now, in this particular case here, we know that dy dt is 1/3, x is 2, and y is this. All right, so putting all those pieces together, let's see, x equals 2, y equals whatever it is. That's more or less here. Rough sketch. And let's see, dy dt is increasing. So which way is this point moving? Y is going up, and it's got to stay on the ellipse. Which way is it going? Yeah, it's going this way. I'm seeing some fingers go this way. It's going that way. So in particular, what you should imagine, so we're trying to find dx dt. So is dx dt going to be positive or negative? Negative, yeah. So when we do out this calculation, we should get dx dt. All right, so let's go ahead and now compute what it actually is. This whole setup here has been essentially to capture that sign to make sure we get the problem right. And so you can understand what's going on.
Could you do this problem without knowing that it's an ellipse?
Yes. Yes, you can certainly do this problem without knowledge of the ellipse. In fact, pretty much everything you need to just cut a narrow path to the solution is going to show up right here. Okay, so here we go. So we need to find some way to relate dy dt and dx dt. Well, the way that they're related is through this equation. And this is the way all related rates problems work, whether they're sort of mathematical problems like this or more real-world problems. You've got some kind of relationship between two things that you'd like to know the rates of. You do implicit differentiation of it to find out how those rates are related, and then you put in what you know and get out what you don't. Okay, so let's see. We need to use implicit differentiation. On 4x squared plus 9y squared is 6. You could also use the other equation that I wrote down for the ellipse. That's fine too. Okay, so let's go ahead and do that. Let's take the derivative now of x and y. Both of them note are functions of t. And we're going to take derivatives with respect to t. So here we go. Take derivative of this guy with respect to t. Well, what's the derivative of something squared? 2 times something, right? So this is 4 times 2 times x of t. And chain rule says you need to write dx dt. Same kind of idea here. It's 9 times 2 times y of t. dy dt. And this is equal to, what's the derivative of 36? 0. Okay. So this is now a relationship between dx dt and dy dt. Now we want dx dt. We've got all this other information. What do we have? Let's underline it and see where we're going here. This is our goal. And what do we have? I'll underline everything we have. We have x of t. We have x. Yeah, we have x. We have dx dt. Oh, wait. Right, I'm misleading you. The goal is over here. Sorry. Okay, so we don't have that. That's what we're after. Okay, do we have y of t? No? Sure? I'm looking at it. We have y? Yeah. We have y. We have the y that we're interested in using. That's right here. That's it. What about dy dt? Yeah, we have dy dt. Okay, and that's the end of the equation. So we, in fact, have enough information to solve this. So now let's go ahead and solve for our goal. So let's see. I'll do this in 2 steps. 8x dx dt is equal to minus 18y dy dt. And so dx dt is equal to minus 18y dy dt divided by 8x. That's formatted back. Okay. All right. So now we just put in the piece of information we have. So let's see, 18 times y. Y is 2/3 square root of 5. And 8x, x is 2. And dy dt. A whole bunch of arithmetic ensues if you so care. You don't need to get full credit on these. Okay? Make sense? Satisfy the need for related rates?
I actually managed to do it.
You managed to do this one. That's great. Yes, sir.
With the graph of the ellipse, within the graph left, what does that mean?
We said dx dt has to be negative, right? Because dy dt is going up, and if you want to stay on that graph of the ellipse as you're going up, you got to go this way. So dx dt is negative, and if you look, whoop, there's our minus sign. So check, we did it. So this at least is believable from the point of view of that picture. I mean, I'm not sure it's believable numerically or not. I think it's right. At least I think we did it right. Yes, sir.
And that's why the 18y. No.
That's why it's negative. Yes, absolutely. In fact, what this equation here, this equation is saying is that dx and basically the product of x and dx dt and y and dy dt are opposite signs. If you will, this is what's actually making you go around the circle as opposed to going off like that. If in fact we have an equation with a minus sign here, instead, what would happen? That minus sign would show up here, here, and flip this to a plus. Then they'd be going the same way. And instead of having an ellipse, if I replace this with a minus sign, I get a hyperbola. So things that go like that. Other questions? Anything else?
Can we do a L'Hopital's rule?
Sure. Do you have one?
No, not in mine.
Does anyone else have one? No. Okay, well, then we'll find one. All right, L'Hopital's rule is section 4.4. So let's see if I define 4.4. Okay. Sure. Do you have a particular kind of L'Hopital's rules? There are several. There's like the infinity over infinity, the 0 over 0.
Infinity over infinity.
Infinity over infinity kind. All right. L'Hopital's rule section 4.4. So, reminder of the idea. The idea is if you're asked to find the limit as x goes to something of f of x over g of x, and one of various bad things happen, various bad situations happen, either f of x goes to 0 and g of x goes to 0. That would be like 0 divided by 0. That's kind of bad news. Or f of x goes to plus or minus infinity. G of x goes to plus or minus infinity. If you're in those, and in there. If you're in one of those two situations, then L'Hopital's rule says what you should do. If you're in that situation, you should take the derivative of the numerator and the denominator and try to find the limit then. As x goes to something of f prime of x over g prime of x. And there are some caveats. F and g both have to be differentiable in order for this to work. If I can't take derivatives of f and g, there's no way I'm going to be able to write down this expression. You better be able to do that. Okay, so that's the idea. Of course, when we talked about this, we were a little more careful about the details. I just want to mostly focus on execution at this point. So let's have a look at problem number 30 in this section. Yeah, sure.
Does it still work if f goes to positive infinity and g goes to negative?
Yep, sure does. Yeah, so the plus or minuses here mean every possible arrangement of pluses and minuses. Yep. Okay. All right, so let's take a look at number 30. This is 4.4. Number 30, and they ask the limit as x goes to infinity of, let's see here, it is natural log of x squared over x. Okay. So, let's see. Which situation is this in? The numerator goes where? Where does natural log of x go as x goes to infinity? What happens to the natural log of x as x goes to infinity? Is it big? Small? Small. Why do you say that?
It's like supposed to be the other way, because I thought about it being the inverse of e to the x.
Okay, so you're right about thinking about the e to the x. It does. Well, let's see what the picture says. Rather than relying on memory, if your memory isn't sound, let's draw the picture. So here's y equals e to the x. Everyone agrees e to the x goes to infinity as x goes to infinity. So it gets big. Now, natural log of x is supposed to be the inverse function. So how do I get the graph of the inverse function? What do I do to it? Yeah, I reflect it across this line, this y of x. So I take this graph and I reflect it. So in particular, this point goes here. This part here is this part here. And so here y is ln of x. So where does natural log of x go as x goes to infinity? Goes to infinity. It's growing slower than y equals x. It doesn't get there very fast, but it does get there. Okay, so this is going to infinity. And of course this, if x is going to infinity, then x is going to infinity. Okay, so this is a situation of infinity over infinity. So that's this rule right here. So what L'Hopital's rule suggests is that we should be taking the derivative of the numerator and the denominator separately in order to evaluate this limit. So limit as x goes to infinity, natural log of x squared over x is equal to the limit as x goes to infinity of the derivative. Numerator to denominator. That's what it says. Okay. So let's compute these. Okay. Okay. So here we go. How do we take the derivative of something squared? What do we get? 2 something times the derivative of something. So we get 2 natural log of x times, what's the derivative of natural log of x? 1 over x. What's the derivative of x? 1. Okay. Well, let's simplify this a little bit. Wait a minute. Did this help? Did it help? Well, sort of. Yeah, that's about right. It kind of helped. It got rid of the squared, which certainly was a sort of a problem. So let's see here. Let's see what's happening on here. Where does natural log of x go? Infinity. Where does x go? Infinity. Oh wait, this is another infinity over infinity situation. Now let's do it again. Now I've got this 2 out front, but I won't let that bother me. Okay. So let's see here. What's the derivative of natural log of x? 1 over x. So this is 2 times 1 over x. What's the derivative of x? Just 1. So if I simplify this a little bit, victory. So what is this limit? 0. This is yeah, this is one of those limits you ought to know. That's 0. So what that means is this guy here, this limit, is in fact equal to 0. So we have to use L'Hopital's rule twice. Here and here. 2 places where we use L'Hopital's rule. But it's a good way to resolve this sort of thing. Yeah?
Can you do another problem that doesn't start out as a fraction?
Doesn't start as a fraction. Sure, yeah, we had a bunch of those. Those are good. Yeah, let's look at 61. This one even has a little bit of a brain teaser kind of feel to it. So we go into infinity, it is. what is this doing? The base is getting bigger, the exponent is getting smaller. In fact, we're starting to take sort of more and more higher powered roots of a larger and larger number. But what do you know about, say, the square root of 2? Is it bigger or smaller than 2? Smaller. What's the square root of, what about the cube root of 3? Is that bigger or smaller than 3? It's smaller. What about the 10th root of 10? It's a little smaller than 10. But do you have any idea if it's bigger or smaller than the square root of 2? I have no idea. It's very tricky. That's what this problem is asking. That's what this problem is asking. It's saying, you know, take the 1,000th root of 1,000. Is that bigger or smaller than the 1,000,000th root of 1,000,000? As I said, sort of a brain teaser kind of problem. Well, it's the sort of thing that L'Hopital's rule can do for you, but after we make a little transformation. Now, this is very similar to one of the sort of problems we looked at a little while ago, where the base and the exponent are both functions of x that are not constant. What do we do then? Natural logs. Yeah, the solution to this problem is natural logs. So the thing to notice is the base and the exponent are not constant. Base and the exponent are not constant. This is usually the suggestion. Use logarithms. If you use logarithms, then you're able to crack this kind of problem. And that's the way we do it. Now, what I'm going to do is I'm going to write it like this. I'm going to give this function x to the 1 over x power a name, call it y, just to make it very clear about what we're going to do with these natural logs. Because we've got a limit floating around. Now, is natural log of x a continuous function? At least for x greater than 0. Yeah, it's continuous. So that will help us because it means that we can either natural log this thing and then take the limit, or take the limit and natural log. It doesn't really matter. So let's let y be this. So we're going to make the observation that the limit as x goes to infinity of natural log of y of x, that's the same thing as the natural log of the limit of y of x. See, this thing here is what we want. We want this. We already know that's sort of a brain teaser to figure out. On the other hand, if we do the natural logs, we can probably crack this. We can do this one. I think that one's kind of hard. So if you will, this is logarithmic limiting as opposed to logarithmic differentiation. Okay, so let's now go ahead and try to address that limit. The limit as x goes to infinity of what's the natural log of x to the 1 over x? So what's the natural log of x to the 1 over x? Well, the great thing about natural logs and powers is natural logs bring down the powers and turn it into multiplication. It turns hard problems into easier problems. So it's 1 over x times natural log of x. Okay, so I just brought this exponent out front. Here it is out front. Left the x of m. Okay, well this looks much more promising. See, now this is natural log of x over x. Now, we just saw a problem like this a few minutes ago. Almost exactly like this, in fact. Where does natural log of x go? Infinity. Where does x go? Infinity. So this is an infinity over infinity. So we should use L'Hopital's rule here and write this guy out as derivative of natural log of x divided by derivative of x. Of course, we've done this now several times. The derivative of natural log of x is 1 over x. The derivative of x is 1. So the whole thing is that. And what's that limit? 0. Okay. So what we have now, that's this equation. So let me summarize that. So we found that 0 is equal to the natural log of the limit as x goes to infinity of this guy, and that guy we said was x and 1 over x. So that's what we found. Now, we don't like that natural log there. We really aren't interested in the natural log of this. We want this. So how do we do that? How do we get the thing in the parentheses? You e it. Yeah. Raise it to the power of e. That'll cancel out the natural log. All right. So this is e to the 0 is equal to the limit as x goes to infinity of 1 over x. And what's e to the 0? 1. So in the end, this limit, which looked kind of hopeless, was 1. So what this is saying, you know, a million to the 1 over million power, i.e. the millionth root of a million, is pretty close to 1, probably. At any rate, the billionth root of a billion is a lot closer to 1 than that. So the answer to that conundrum is this thing. Tends to 1. That sort of answer your question? Yeah, I see some questions here.
Oh, no, I have another question.
You have another question. Question on this?
Oh, yeah. Is this all
Yeah. Yeah. Other questions on this before we move on? Okay, sir.
Yeah, can you help me finish a problem where we find code 4? It's
Sure. Hold on a sec here. Which problem? 5.4, number 55. Sure, this sounds like an integral kind of question. 54? 55. Okay, so this is a marginal revenue function. 5.4, number 55. What's the problem, Rick?
It says the integral from 0 to 11 square root cube root of 1 plus 7x x.
I have a feeling that's not section 5.4. 50. Ah, no, you meant 5.5. Oh, that. Okay. Okay. All fives. All right. So this is the integral from 0 to 1 of cube root of 1 plus 7x dx. And your job is to evaluate this. Okay. So if you want to evaluate this integral, let's see here. It's not the sort of thing you want to write a Riemann sum for if you can avoid it. That would be kind of dreadful. So we don't want that to happen. I mean, all those cube roots make it very awful. So you said, can you help me finish it? Presumably you've got a substitution in mind. What substitution did you want to try?
Maybe taking out root, or bringing u equal to 1 plus 7x.
1 plus 7x. I think that's a good choice. Let's go with it. So I took derivative of this. if you will, if you think of this function as u as a function of x and take du dx, I would get 7 as the answer, and then just push the dx over there. Okay? Well, let's see here. I don't have 7 dx's, I've only got one of them over there, so 1/7 du is dx. So I can replace dx with du, and I can replace the x expression with a u expression at the cost of just having to put in a 1/7. Okay, so let's do that. So this whole thing is equal to cube root of, this is what we chose to be u, cube root of u. The dx can be replaced with a 1/7 du. And now the only thing that remains is I need to change these limits, because these limits are x equals limits, and I'd like some u equals limits. So let's see, I just basically said x is 0 here. So if I put in 0 for x, what's u? 1. No. And if I put in 1 for x, what's u? 8. No. Okay, so I've transformed the problem from an x problem into a u problem. And everything, this is a definite integral, everything is in terms of u, so I don't have to look back. I can just go with this and never remember that I was dealing with x's. Okay. So let's see here. If I simplify this ever so slightly, maybe I should write this as u to the 1/3. Okay, now I want the antiderivative of u to the 1/3. I mean, at this point, I could even try to write down the Riemann sum. That's probably a bad idea. So what's u to the 1/3? What's the antiderivative of u to the 1/3? Or answer the question, what function do I have to take the derivative of to get u to the 1/3? Yeah?
3/4 c to the 4/3.
Yeah. And how'd you get that?
You would do 1/3 plus 1.
1/3 plus 1 up here.
And then I reciprocate the fraction, but
Yep.
it's like, yeah.
Yep. So what's 1/3 plus 1? Well, that's 1/3 plus 3/3. You say, yes, that is 4/3. And so if I were to have forgotten this coefficient out front and taken the derivative of this, I would have gotten 4/3 u to the 1/3. But I don't want that 4/3, I want to get rid of it. So I put a reciprocal there, 3/4, to make it go away. Okay, so this now I'm going to evaluate between 1 and 8. So I just need to go ahead and do that. And that just takes us a few seconds to write that down. So I'll do it right here. So this is equal to 1/7 times 3/4. And when u is equal to 8, 8/4, and then minus, what's my other limit? My other limit is 1 to the 4/3. Now, I'm perfectly happy if you leave that as an answer on the exam. If you want to simplify it, it's perfectly reasonable to do so. Let's see, I guess it's 3/8. What's 8 to the 4/3? Sounds kind of imposing, but let's see here. What's the cube root of 8? 2. And what's 2 to the 4th? 16. Now what's 1 to the basically anything? 1. So this is 3 times 15 over 28. 3 times 15 is what? 45. This is 45 over 28. So not too bad in any event if you try to do the arithmetic. As I said, leaving it like this, totally fine. Yeah?
Would you get the same answer if you subtracted, if you plugged 1 into that whole equation and subtracted that from,
Plug 1 into just
when you're evaluating it for 8 and 1, instead of doing 8 to the 4/3 minus 1 to the 4/3, if you did.
Oh, I see. Are you asking?
Minus,
because what did I do to get here? I just took out this common factor. Yep.
If you
Oh,
did it the other way,
What's that?
if you did it the other way, as in like if you didn't change the limits,
Didn't change the limits.
then
Yeah.
where would you stop?
Okay, let's do that. Yeah, you don't have to change the limits. It's really fine if you don't want to.
Okay, I got the same answer.
What's that?
I got the same answer.
Yeah, you should get the same answer. And basically the point is you stop at about the same point. So if you don't change the limits, so if you leave the limits alone, that's an option. So what you could do is where instead of writing it like this, we'd be at that stage. I'm leaving the limits off of the whole problem at this point. I still come up with 1/7 times 3/4. Now, this is u to the 4/3, just as before, plus a constant. But now I have to put it in terms of x. So it's 1/7 times 3/4 times, now what is x, right? So it's 1 plus 7x. 4/3 plus c. Now I come back to my original formulation and now put in limits. What is my upper limit? My upper limit is x equals 1. And my lower limit is what? Yeah. So this is the situation I'm in. But if you do this, you look at it and you say, oh, well, what's 1 plus 7? That's 8 to the 3/4, 4/3 rather, minus 1 plus 0, that's 1. Oh, that's the same thing. So either way it works out just perfectly fine. Okay. So take your pick. It doesn't really much matter. Okay, we've got 5 minutes left. Yes, sir.
I don't know if I have enough time to go through an entire problem like this, but I was thinking about the problems where we have to draft the function from, it was like from section 7.
Yeah, so it was a curve sketching kind of situation. Right. Yeah, probably do not have time for that. But let me sort of remind you what goes into that. There are all sorts of problems like this. Summary period, yeah, you're right. It was 4.5 is the curve sketching section. So, sketching. Section 4.5. And if you remember, I had little set of instructions or set of suggestions for how to proceed. First, proceed by symmetry, see if there's a symmetry. Then go ahead, if it's polynomial, try to factor it. If you can factor it, that's great. Then go ahead and start computing limits and derivatives and try to aggregate all that information. So that's the procedure. So let's take a stab at a problem here. Let's have a look at number 16. I don't think we'll finish it, but we'll have some idea of what it looks like. So your task is sketch this. So let's see here. First of all, what do we know about this problem? Well, are there any places where this thing's got to have a vertical asymptote? 0, yeah, 0 is a vertical asymptote. Is there any symmetries in this problem? If I put in minus x, for instance, does anything nice happen? Not really, because this becomes negative, this stays positive. So no obvious symmetries, really. So no even odd symmetries. What about horizontal asymptotes? As x goes to infinity, where does this function go? 1. Yeah. So this has a horizontal asymptote. So y equals 1. You say horizontal asymptote. Now, are there any roots of this equation? Places where this equation is equal to 0? I think the answer is yes. I think we might be able to find, at least guess at something. See, if I move much of this stuff, if I multiply through by x squared, what do I get? X squared plus x plus 1. That's a quadratic. I should be able to solve that. X is negative b plus or minus b squared minus 4 times a times c over 2a. Uh-oh. Red chalk is perfectly placed. What does that say? No roots. No roots. So 0 is a vertical asymptote. We've got a horizontal asymptote. Here's our horizontal asymptote. Here's our vertical asymptote. There are no places where the function is equal to 0. Now, when x is greater than 0, is this a positive or a negative number? It's 1 plus a positive number plus a positive number. And not only is it positive, it's greater than 1. Now, what about over here on this side? This is 1 plus a positive number, plus a negative number when x is negative, plus a positive number. Which of these is going to be bigger or smaller? Well, remember, we never can cross the x-axis. There are no roots. Eventually, it's going to go to 1, right? Eventually, when x is like negative infinity, this is 0, that's 0. So like eventually, we're here somewhere. And we've got a vertical asymptote, so we've got to like go up this way. The only thing that might happen, and it's the sort of thing that we don't have time to trace down. I think it does this. I think it does this. So how do you find this? By half. Take a derivative. Yeah. So we haven't used. Thus far, we haven't used the calculus. Now we need to use the calculus. Places where y prime is equal to 0. And are there any such places? Well, actually, y prime is pretty easy. Y prime is negative 1 over x squared minus 2 over x cubed. And I think there are some zeros. What's that? It can cross a horizontal asymptote. That all the horizontal asymptote says is that it's going there as x goes to infinity, or negative, which it does. Okay. Well, it's been a great semester. I want to say you guys have been fun, and I hope you do well on the exam. Reminder that I have office hours next week, Tuesday and Wednesday, 10 to 2. You can come see me. Of course, you can come visit me anytime you like, really. Just send me an email. I'd be happy to see how you guys are doing. Good luck. Thank you.
Thank you.
You're welcome.